All right, line W1, learning test 2, we're going to take a look at DC power converters. Now, some of you are already writing this off as being, I'm never going to touch a DC motor in my life. I hate to break it to you, but a DC power converter is used inside of both my DC drives, as well as it's going to go and be used inside of my AC VFDs, variable frequency drives. It's going to be a component that is going to be inside of both of them because AC VFDs are just going to create synthetic AC, but they have to do so out of DC, which means that the incoming AC has to come in, it has to get converted, and then we're able to either go and create the synthetic AC, or we are able to go and use it to drive our DC that we're going to go and have inside of here. Now, we've talked about rectifiers back in the beginning of this year when we were covering electronics, the three-phase rectifier. We saw that we had two main types. We had the three-phase half-wave rectifier, and we saw that we had the three-phase full-wave rectifier. The half-wave rectifier only would have a single one of these that would be active at any point. We'll say that those two are blocking, and that we've only got this one over here that would be in conduction, which would mean that we would have a small amount of voltage based upon my phase. I've only got a single phase that is going to be active at a time, therefore this voltage over here is going to be based upon that phase being rectified and passed through. If you compare that with your full-wave bridge rectifier, your full-wave bridge rectifier is going to go and have two that are going to be active at any given time, and then two that are going to be blocking these two, and then two that are going to be in between, and therefore they're ignored. They're neither the most attractive place for electrons, nor the least attractive. They just kind of get ignored. They're blah inside of there. So what we have in this case is that we are going to go and have a system that is going to be able to go and pass through like that. And what we see is that on this one here, the full wave, we're going to be passing through line-to-line value of voltage, rectifying that, passing that out to the load, which means that we're going to be dealing with a higher value of voltage. Now, these two that we're looking at over here, the half wave and the full wave, both of these are going to be based upon diode bridges that we see over here, right? Oops, sorry, wrong direction there. We see that they've got diodes inside of here. What we can do is we can go and change these diodes for SCRs. And if we go and change them for a SCR, we will then be able to go and control the amount of current that we will go and pass through, because we're going to be controlling the amount of time that we are going to go and pass the value of voltage, and therefore the average value of voltage inside of these. So, going into what we'll cover over here, we're going to start changing these. In some cases, we will just use diodes to rectify into DC, and then we'll go and chop that DC up. In other cases, we're going to go and use SCRs to adjust it into variable DC that we're going to have. Either way, no matter how we go and create it, whether it's half wave or three phase, we're going to go and have two things that are going to be in common. The first thing is we are going to go and have this. Now, I don't know if you remember trying to calculate ripple values of voltage, but ripple voltage is just going to be the amount that might pass through waveform, which is represented by this line that I see over here. That's what's passing through. We see that that stays always above my 0 over here, so it's a DC waveform. That's going to be called my ripple voltage. And the ripple voltage is not going to necessarily be a great thing for us. Same with that ripple frequency, right? We see that we got this ripple frequency that is going to be 3 times whatever my source was. If I have 60, then I'm going to go do 60 times 3, and I'm going to go and see that I get 180. That is going to be my frequency of my output ripple on here. If I go to the full wave rectification, same deal. I'm going to have a value of ripple voltage. That's going to be, top of the humps to the bottom of the valleys over here. That is going to be smaller off of a full wave, and I'm going to go and have a much more rapid frequency that's going to come off of here for that ripple value of frequency. You can, in some cases, go and filter that out. If we do try to filter it out for a very large drive where we have to pass a lot of volts and currents through there, it makes for really large components that we would have to utilize, huge inductors and huge capacitors, because those are going to be the two ways that we filter stuff out. You can go back into your second year electronics and we cover filtering, with the different types of filtering, and it would just be applied in the same way into a three-phase circuit. If we go to a large one, a very large DC demand, whether that's going to be for a large VFD or whether that's going to be for a large DC drive, we want to go and have the absolute minimum amount of ripple and the higher ripple frequency because it's closer to a straight line, right? If you go through a bunch of small bumps really fast, it's closer to that. You feel less than if you go over top of a large, set of bumps. If you've driven logging roads before, you get those points where it's washboard. If you hit those washboards fast enough, it's a bit dangerous, but you don't feel them as much because you're just bouncing over top of them so fast. Because of that same sort of effect, we want to go and have this on large DC drives. We will go and use this full wave rectification. We're going to go and use thyristors to go and power everything forward. We're going to use those SCRs that we talked about, and then we're going to start chopping stuff up. Let's talk about single phase first, and then we're going to go and take a look at three-phase that we are going to go and have. On single-phase types of systems, this is what we will see. We're going to go and have a fixed field supply. We are also going to go and have a non-fixed value that we're going to go and pass through. Now, I want to point out a couple of different things off of this. First of all, this over here, this is just simply going to be used for suppression. This is a TVSS, and it is there to go and deal with any sort of spikes that come through, because we know that anytime that we have got a spike, we have got this dV/dt, right? You should remember that from SCRs, and it's basically anytime that I get too sharp of a leading edge coming off of my waveform, then it's going to go and accidentally trigger these things. And I don't want to trigger these things particularly. I would never want to go and trigger this and this together, because if I were to take a look at that, that would then become a dead short that I would have across. So we've got this inside here. That's just going to be a filtering element. It's connected directly across line to line, and it's designed to go and just pass only the high voltage section, stuff that's over top. It's based upon a value of voltage and upon this speed that it's going to have, and it's just going to pass those through. Any little blips that we get off of the system get passed and filtered out of there. My actual components themselves are going to go and pass values of AC and DC through. You should be, we'll start with the diode over here. You should be familiar with the fact that this part up here, the line is called the cathode. The other one's called the anode because it looks like the top part of an A over there. And it is going to go and pass, if I take a look, this one will pass a negative through to down here. So that's going to be my negative side. This over here would be my positive side. If I take a look at my field winding, I see that my field winding is connected across from here up to there. So it's only partially connected through here. It does receive constant power because any time that either this line is negative on my AC, or anytime that this line is negative on my AC, there's always going to be a negative over here, which means that this will always get a negative through here, and if one of these is negative, by law, the opposites over here, the other one would have to be positive, and if this one was positive, I would then be able to go and pass a positive value through the SCR that would be attached over here. Oops, sorry, wrong one. Hold on. I highlighted too many lines. Give me a second. I've actually highlighted the wrong line off of this one because we only get this field supply that is going to be active for a single pulse. Right now, the one that I've got drawn over here, that's why for a second I was like, oh, what's going on here, is we drew this so that if this is negative, this is positive right now. Right now, if this is negative and passing through to here, to that connection, if this is negative over here as well, there is zero potential difference, so I'm not going to go and have any sort of current that's going to pass through that field that I'm going to have. But when I alternate, let's just do that real quick over here, positive, negative, like that, I'm still going to pass a negative through down to here, but I'm going to have a positive over here, which means that I would have a complete path for current flow going through and to that point over there. So for one of my alternations, I'm going to go and pass current through here. For the other alternation, I'm not going to pass current through here. It is going to go and have a half-wave rectified single-phase input, is what this field over here is going to go and see. Now, because it is an inductor, that means that it is going to go and smooth out. It's going to go and drop down by collapsing those lines of flux that it stores around itself back in. This thing is just going to be powered off of those connections there. So it is going to receive constant power as long as there's power feeding into this drive. This thing is going to go and pick up the positive, negative, and then it's going to block the opposite positive, negative. Okay, that deals with our field. Let's take a look at the armature. The armature is going to go and receive power through here as well. Same deal, we're always going to have a negative that's going to be passed through onto here. But then we're going to adjust the amount of positive that I am going to go and have. Now we've got 3 lines going to the triggering circuit. This one over here is going to be a reference telling me what's actually happening. These 2 are going to be based upon the reference. They're going to be inputs back in to go and gate this SCR at the correct time. And so what I'm going to go and have is the ability to go and take a full wave rectified DC. That's what I would normally have out of here. I can take that full wave rectified DC out of there, and I'm going to, through these SCRs, just adjust the firing angle. So I can go and have this, like that, which would give me a lower average value of voltage. And if I were to go and chop away more of the waveform, draw it one more time, I'm going to go and have, once again, a lower average value of voltage that I would have out of this. And because it's working off that average, nothing, and then a little blip, nothing, and then a little blip, nothing, and then a little blip, the amount of average voltage that I have over top of this would therefore be smaller as well. So all we're using these 2 SCRs for is to go and control how long we're applying the rectified DC. They rectify and they control, and that's going to go and pass my power through to the armature itself. This one does not have the ability to go and reverse the motor inside of here. We're always going to go and have a positive and a negative that's going to be applied to it. I would have to have different type control for me to go and change that into a reversing direction. We're not going to draw that one in here. We'll take a look at our next one instead. Freewheeling diode over here. Freewheeling diode is just for the points where we're not conducting. So if I just erase some of those over there, like that. At these points where we're not conducting, we're going to have provided power through, and then this thing is going to have windings, which are going to act as inductors. So they're going to be collapsing their lines of flux back in, trying to maintain the direction of current flow. When they try to maintain the direction of current flow, they change this thing into a source. So I'm going to go and have current flow through the source goes from positive to negative, which means that this is then going to be able to drive its current back to that freewheeling diode. It's just going to go and snub off any sort of induced voltages that would otherwise try and get fed back into these SCRs, giving us that DVDT that would otherwise cause erratic firing off of these ones. We can go to a full wave converter. Over here, the first one that we saw was called a semi-converter because it gives us full wave rectified voltage for the armature, but only half wave rectified voltage for the field. This one over here is going to be full wave that I'm going to go and have. I've got a small transformer that is over here. It's going to be center tap biphase. We're going to go and put that into a bridge rectifier, and then we're going to go and have full DC rectification across the field itself at this point. So I'm going to have a higher value of field voltage, more flux, which is going to go and give me more power that we'll have out of this thing. And then I'm going to go and have my single phase supply that is going to be fed in from here. Let's go with positive, negative right now. And this single phase supply, I've got 4 SCRs on here, which leads to some exciting possibilities where I can choose what I'm going to go and fire through here. Let's pick a pair and fire some voltage through. Let's go and say we got positive being placed into here, and I'm going to go and fire this one. This one is going to be fired. This one would be off right now. And then I'm going to go and take a look at this one over here. I'm going to fire this one, and then this one would be off over here. And so what I can do is I can take that, and I can drive that through like that. We've got current that is going to be traveling up through from A2 over to my A1 over here. It's going to allow me to go and control that. As soon as my AC alternates, negative, positive, we would change which ones of these are going to be conducting. This one would be blocking, this one would be conducting, this one would be conducting, this one would be blocking. And as a result, we'll just draw one more arrow over top of this thing. My current is going to come in, and it is going to, wrong line there, my current is going to come in on this negative over here, and this one is now conducting. It's going to travel up and through here, and then it is going to come out on this positive down to this one over here. Same thing, we get DC current that we're going to be able to pass through, and we're going to be able to go and fully control it. But we've got a bigger version of the motor. Instead of the semiconverter, we're getting a full wave converter where we get maximum flux, as well as we are going to go and have maximum amount of rectified voltage that we would have through our armature that we can get out of here. With the addition of an additional 4 SCRs, I would also be able to go and set this thing up for 4-quadrant operation, where I would be able to go and use the first set of SCRs like this to go and create a positive and a negative, and then I would be able to go and use an additional set of SCRs. How about, actually, I'm just going to move all of this over, and then we will draw that. 2 seconds. Let's just erase this. These over, and then we'll draw how we change this full wave converter into an actual reversing full wave converter. Reversing full wave converter is going to go and take AC in. It's all going to be done up here on the armature control, because that's the component that we want to go and reverse. Where I'm going to go and take in, I'm going to have a set of SCRs done the exact same way. So we're going to go and use these that are going to go and convert my power. Okay, so these ones here are going to go and convert my power into my DC. We'll stick a positive rail up top here. We'll stick a negative rail down below here. What that allows me to then do is I can take that and I can run that through another set of SCRs over here. These SCRs are going to be biased in the opposite direction. Just draw all the way out to here and to here, where I'm now going to go and be using these for load control. Let's go like that, over there, here, here, and here, where I'm going to go and have sets of SCRs that I'm going to now have my armature gets connected across the center, like that. Obviously, this is just going to be terminals, leads that are going to be brought on the board for that. But what these ones do over here, the ones highlighted in yellow, is all that they need to do is they need to go and create my value of DC, positive, negative. These ones over here, and they don't actually need to be SCRs. You can use just straight diodes to get DC out of there. These ones that we have over here are going to go and gate in pairs to drive currents through. So if I've got a negative down here, what I can do is I can go and gate with that negative here. I can send current through the armature like this. Use these ones over here. If I want to vary the speed, use these ones here to vary the size of the voltage that I have out, and use this set to drive that forward. And if I want to go and drive it in reverse, I would just go and energize the opposite set. Now I've got current going through the armature in the opposite direction over here. This is referred to as a H bridge that we would have off of here, where it's just driving current through in the opposite direction. This yellow one here is going to control the amplitude. This other H bridge over here just controls the direction off of these. Makes this a really, really useful component, because now your DC motor can be solid state driven into forward and into reverse at any sort of varying speed. Moving on down through here, they give us 3-phase full wave semiconverters that we have, and then we have got 3-phase full wave converters as well. Semiconverters are less commonly used. You might find them in old installations. They just are still kicking around, haven't died, because a lot of our semiconductor components will last a fairly long time if we don't have spikes, if we got good quality voltage on there. But a semiconverter basically had 3 SCRs and 3 diodes. Semiconverter was just meaning that this thing was only converting part of the wave. These other sections of the wave were all going to be passed through to my negative I would have over here. This was going to just be controlling what I would have on the output. Was not my best value for the money, or my best control that I would have. So as prices came down, we went to full wave SCR converters. This is going to be no different than what we saw at the very beginning, where we saw, oops, sorry, wrong one there. 3-phase full wave rectifier. Instead of us having a 3-phase full wave rectifier, we now have got a 3-phase full wave SCR converter, where I've got SCRs in place of those diodes, and I can go and chop away as much or as little of that waveform as I want. And this is all just done through timing the pulses that are going to be coming into my SCRs. They show we've got our 3-phase lines feeding in over here. We feed them into the SCRs, and then these SCRs are going to go and get pulses that we are going to go and fire them to. And as we fire these pulses, our pairs of SCRs, we are going to be able to go and pass voltage through in certain directions. Taking a look, we're not going to go through every blip on here, but if I follow these down, this is a timing diagram across the bottom over here. I know, we love them. That timing diagram shows that we have got only 2 SCRs that are fired at this point. The other ones, if they're not fired, they're going to go and be blocking. So I'm just going to go and put check marks next to the 2 that are shown as being fired. That's going to be my SCR3 over here and my SCR5 over here. And then I'm going to go examine those as far as the lines themselves go. Right now, if I take a look at that, my lines are going to be based off of these ones over here. Why don't I just highlight the lines first? We'll use our proper 3-phase colors for that. The lines themselves are not delineated. It helps to understand this. You know, if we were to actually put these on here like that, and then black is going to be my middle one there. We'll leave that one. I won't highlight over top of it because things just start getting messy, but black should be this next one that starts over there. And then the last one that is going to be starting another 120 degrees past that is going to be C, this one over here. Highlight that one backwards over here, and then we will highlight that one forwards over here. So what we are seeing inside of here are those 3 waveforms, my A, B, C. And if I were to take a look at now the timing that I've got this thing fired into, the timing is going to be right over here, like that, where I'm going to go and have a firing at this point that is going to be my CB. What we want to do inside of here is we want to just carry along the maximum value of voltage that's going to be possible for us to see. And the way that we do that is really we've got to take a look at our standard 3-phase waveforms that we are going to have. And I just want to take a look, and I just want to say we want to surf the top and the bottom lines of these ones over here. If I look at this, I see that my actual 3-phase waveform looks like that, going across from point to point to point to point to point across the top over there. And if I were to look at this thing on the bottom, I would see that this thing is going to be going like this over here. And that is the line that we want to go and surf, because that is going to go and give us the maximum displacement. In other words, at all times, we want to be in between the top line and the bottom line. And we're going to have to go and change components in order to go and do so. So looking at this section that we have here, I'm just going to erase those over there. Looking at this section that we have over here, we see that right now we want to be between the black phase, that's our B phase, and our red phase, right? This is the top line over here, this is the bottom line, so I want to have be between my A phase and my B phase. And if I take a look at that, I see the only 2 SCRs that are gated on. I'm gating on my A phase, that's this one right over here. The A phase is gating on for its positive over here, and my B phase is gating on to be the negative right now, so that I'm going to have a maximum positive, maximum negative. And then as I move along through time, I would see that the next point that I run into is going to be now where A is still really positive, but now C takes over B as being the most negative, which means that I want to go and fire to become A and C. Once again, I'm going to go and keep A positive, SCR3 over here, and now I'm going to go and fire the C negative, this one over here. That is going to become my negative. And so if I pass that through, I would see that once again, my A fires the positive, but now it's going to be my C that is going to go and fire the negative. And we have to do that every place that this thing goes and goes and changes direction. Right over here, that's where I would fire the next one, because now at this point, I'm going to have B that is going to become my most positive, while C becomes my most negative. So the C one stays fired, the B one would then go and fire, and we would see that it would be SCR2 over here that would be fired. And so really what you can do, if you take a look at it, is I'm just going to draw a green line over here. What we are really looking to do is we are looking to go and create this green line over here. And I don't know if it'll let me select it. Please select. Oh, beautiful. If you take a look at that green line over there, that's going to be my magnitude of voltage. And you can see how this thing stays the same magnitude of voltage, because it's just switching line to line as it goes across, up and down, up and down, up and down like that. It's a pretty cool thing. All we're doing is we're just switching from component to component. We just are monitoring what's the top line, what's the bottom line, and then triggering these SCRs at the same time. Okay. Now, what we were just looking at over here was if we were going to go and pass the maximum value of voltage that we would go and have, available through here at any given time. That is great when I want to go and get maximum power out of my DC converter, but if I decide that I'm going to go and change the firing angle, and instead of firing everything right at the very first instant that it passes right over here, I might decide to wait a little bit, and instead of passing that thing all the way through right at the very beginning, I wait a little bit, and what's going to happen then is I'm going to go and have a shorter amount of time that I conduct that wave through. That's what they're showing over here, is that we have got times that we change our amount of power that we are going to be rectifying and passing through off of these ones. Now over here they're showing us DC outputs. This over here is where I have got a small firing angle. Basically the amount of DC that I'm going to be generating is going to be a relatively high, almost at my peak value that I'm going to have out. But as I increase the firing angle, what happens is the amount of power that I'm passing through, just looking at just the top side over here, is going to go down. And as a result of that, we're seeing that the average value that we're seeing is going to be going down, right? We have less time that we're conducting with a small or a larger drop inside of there. Therefore, we're going to go and have a smaller magnitude of DC. Over here, we've got less. We're going to have a smaller magnitude of DC. And we can get to this point right over here, and this is a critical point on the graph, where I'm going to be at a 90-degree delay angle. When I get to a 90-degree delay angle, I'm only going to be passing through a little blip on the top, but I'm going to be passing through an equal-sized blip on the bottom. At that point, my average amount of DC is going to go and be a positive and a negative that are simultaneous in values. Therefore, it gives me an average value that's a 0 for my DC output. If I then go and change my firing angle all the way down to 120 degrees, fire this thing really late, then what I'm going to have is I'm now going to be going into the negative region off of these ones. And if I go even further, past that 120, I'm at 150, I'm going to be able to go to a negative value that's going to be completely in the opposite direction. Really what this will do now is I have reversed my value of DC that I'm going to go and have on the output. I'm going to have a certain amount of phase shift range that is going to be based upon the controller's physical component, the speed of operation, what we call the propagation delay of the electronics, all of that stuff combines together to create this. So that's going to be this to this over here. Somewhere in between those two ranges that we are going to go and have. This phase shift that they're showing here is for this specific set of controls that we have over here. If we reverse the amount of voltage, if we reverse the voltage while still maintaining current in the same direction, we're going to go and have regenerative braking. And it's shown inside of here. It's a whole other set of lessons to go through just talking about regenerative braking. We've talked about it just on the surface, and we're going to keep it on the surface at this point because we don't need it to pass through third year. Just understand that anytime that I've got forward voltage while having reversed current, I'm going to be able to go and create regenerative braking where I'm feeding power back into my supply. All right, that is it for this one.